Hi everyone, I'm Mikael Z Lagerkvist, and I'm presenting the paper Half-Checking Propagators that I wrote with Magnus Rattfeldt. As you see, neither of us has a stated affiliation. This was work that we did privately because we found it interesting. The genesis of this work is a simple idea. What if we allowed propagators to propagate too much? To potentially remove solutions, to actually be incorrect. What would this mean? And perhaps more importantly, is it useful? Shortly, that would mean that propagation would no longer be correct. And therefore, solving would become incomplete. However, it could give us more propagation, and as we all know, more propagation is always interesting. The paper is a long exploration of this basic idea, and in this presentation I will attempt to show you what the idea is, give some idea what it means, and also some examples on how it could be used. It's fair to warn you though, that while we believe in the idea and its potential, our experimental evidence is not super convincing yet. So, without further preamble, let's dive into the details, and let's start with some background. Propagators are awesome. They really are. They enable us to combine many different algorithms using smart propagation, and they are a key to the success of constraint programming. Propagation is the bedrock that we build our solutions on. But designing propagators is hard. First of all, the algorithms must never remove a solution. Also, propagation is fundamentally a co-NP style problem. Propagation needs to prove that the literal is in no solution. Personally, I find co-NP to be more complicated to reason about. What is half-checking propagators really? In order to answer that, we will need to define what a propagator is. First of all, a propagator is a function from domains to domains with a certain set of properties. The first property of a propagator is that it is local. This is the trivial property that it can only modify its own variables. If you have x less than y, the propagator will not modify the z variable. Second, it is a contracting function. That is, it can only make a domain smaller. Thirdly, it is checking. For an assignment, the propagator keeps it if and only if it is a solution to the constraint. Put another way, a checking propagator can identify if an assignment is a solution or not. Lastly, propagators must be weakly monotonic. This means that if a domain contains an assignment that is a solution, then that assignment is not removed from a larger domain containing it. There are a lot of variants and stronger properties that sometimes are used, but these are the minimum properties needed to make propagation well behaved. With that definition of propagators, what is a half-checking propagator? A half-checking propagator is still a function from domains to domains, it is local, and it is contracting. For a half-checking propagator, as can be heard from the name, the checking property is weakened to only go in one direction. If a propagator says that an assignment is a solution, then it is a solution to the constraint. We can have false negatives, but not false positives. Furthermore, we remove the requirement that it is weakly monotonic completely. Taken together, this allows a half-checking propagator to actually remove solutions. Also, it is allowed to do so in a non-monotonic way, which means that a larger domain may lead to more propagation. Formal definitions are important, but we also need to know what they mean. What does it mean to have propagators that can remove solutions? As mentioned before, solving a problem is no longer complete. We may miss one or even all solutions. This is common in other incomplete solving methods also. The difference here is that we've lifted incompleteness into the actual propagators. The real upside is that a half-checking propagator could actually propagate more than a domain-consistent one, or at least incomparably so. Actually using half-checking propagators in a real system requires some thought. First of all, a system that uses recomputation may need to take special precautions. These are the same as for supporting weakly monotonic propagators, so that is often okay. Testing becomes more complicated since there are fewer properties that we can use. Portfolio solving can be used to regain completeness. However, care must be taken with no-goods, since they are no longer globally valid. An asset that aims to be complete cannot use a no-good from an asset with half-checking propagators. So far, I've talked quite abstractly. In the paper, we have 3 general ideas on how to design half-checking propagators, and for each one, we've applied it to the cost circuit constraint, which models the TSP problem. The first technique is based on lifting solution dominance relations into a propagator. Our example for this is to remove crossing lines in 2D Euclidean TSPs. Note that while this is sound for a pure TSP, additional constraints could make this incorrect. The second technique is based on bounding a cost based on heuristic solutions. Here we use a variant of the classic Christofides-Serdyukov algorithm to find a bound for a metric TSP. Similar to the previous technique, this is sound for the pure problem, but not so in the presence of other constraints. The third and most general technique is based on finding literals that we guess should not be part of a solution. For cost circuit, we used a one-tree construction and made some small heuristic deductions from it. This technique is not even sound for a pure TSP problem. Unfortunately, while we did get more and complementary propagation using all 3 IDs, we have not yet managed to thoroughly prove that we actually solve problems faster. One of the problems we had with this has been to properly handle no-goods in our portfolio setup. We think that half-checking propagators is a new and interesting idea, and that we as a constraint programming community should explore it more. Part of that exploration naturally needs to be how our technique relates to other incomplete methods. Importantly, this is not a competition, there can be synergies. The most closely related technique is probably streamliner constraints. The important difference there is that all propagators added as streamliner constraints are normal propagators. Additionally, it works on a model level and not on a general constraint level as half-checking propagators do. Finally, I think that belief propagation and cost propagation are both very promising techniques, and these have so far only been used to guide search. Using them for propagation would be a natural use case for half-checking propagators. To summarize, we introduced a new idea for incomplete solving that we called half-checking propagators, lifting incompleteness into propagators for the first time. This can, and probably should, be combined with other techniques for incomplete solving. A large problem that we encountered is that no-goods needed to be handled very carefully. And finally, all the code is available on GitHub. Thank you for listening, and I hope that some of you will keep this technique in mind the next time you design a new propagator.